Thanks for inviting me to give this talk on the use of digital PCR for diagnosis and quantification of viruses. First, I must say that probably some of you wonder what the heck is that? What the heck is digital PCR? Or you know that PCR is just a procedure of amplification of a template using a mixture of primers probes in the case of qPCR and enzymes. And so you have one PCR reaction, and then after the amplification, you develop the result with a gel in traditional PCR or with detection of fluorescence with RT-PCR. In the case of digital PCR, we are working also with a PCR mixture, so it's exactly the same. But in this case, we are going to distribute this reaction in thousands of reactions, in thousands of partitions. And the best way to understand it is using the graphical view of one of the systems of digital PCR, which is a honeycomb of in between 1,000 and 5,000, depending on the system, of cells, microcells, and then the distribution of the PCR mixture into those cells make us to get thousands of drops. Each drop must have one or no more than two templates, or of course, non-template. And so we can ensure that the distribution of the population of templates follows a Poisson distribution. After the amplification, we are going to obtain a number of drops with positive fluorescence. We use, let me go back again, we use labels, two labels for labeling two types of templates. So after the amplification, we are going to obtain two types of fluorescence, two colors, and this kind of graph, where we can see clouds of black drops with no label, clouds of drops with any of both original colors, those corresponding to template 1 or template 2, and clouds of drops with a mixture of both, a mixture of the color. Counting the number of drops of each color and applying an algorithm for the Poisson distribution, we are going to be able to calculate exactly the number of copies per reaction in the sample, and in both cases for both templates. Therefore, this is an absolute quantification, which is the first difference with respect to the qPCR, which needs standards for to apply a relative quantification. This might look like a futuristic technology, but I must say that it is not. It is quite old, not at all, of course, because it is from the late 80s when a group of Seiki decided to demonstrate that they were able to amplify a single molecule, a single genome. And they needed to demonstrate that they were working with single molecules using a Poisson distribution. So they apply limit dilutions, and they demonstrated that the last dilutions had only one or two templates, and obtaining positive results with those samples, they were able to demonstrate that they could detect a single molecule in a sample. And this was the aim of the new reports in the following decade, the single molecule detection. And this technique was called like that, single molecule detection, because the first time that the term digital PCR was introduced was 1 decade later, in the late 90s. A group who they decided to quantify, use the same technique that it was being used before, but this time to quantify the number of copies in a mixture. You applying dilutions and distributing the PCR mixture in the wells of 348 well plates. Later on, this technology was called digital PCR, and it was used not only for detection but also for quantification of templates of genomes. In these times, and also at present, This technology is used most frequently for early detection of cancer, of certain types of cancers. The first time that it was used for diagnosis of viruses was in the early 90s for detection of proviruses of human immunodeficiency virus. And in the last decade or so, it has been increasingly used for diagnosis of viruses, for diagnosis and quantification of viruses of a large number of families and from all the Baltimore classes, as you can see in this slide. Well, this is because we have many more advantages of the digital PCR versus the qPCR than disadvantages. The disadvantages can be the prices, for example, and the much higher research that you have to apply to be sure that the advantages of the digital PCR are applied. Disadvantages are first and most important, the extremely high sensitivity. High sensitivity is understandable if we consider that we are able to detect a single template within a single drop within the PCR mixture. Well, theoretically, the qPCR is also able to detect a single molecule, but the best sensitivities that I have found in the literature and that we were able to obtain with qPCR was 1.5 templates per reaction, which is quite high, but it is not that high as we can obtain with this technology, as I'm going to show later. The second characteristic, the second advantage of this technique is that it represents an absolute quantification, which means higher precision, which also means high accuracy with better results in repeatability and reproducibility, and of course, more reliability of the quantification. And it has another advantage comes from the fact that instead of one reaction, we have thousands of reactions. So the presence of PCR inhibitors is going to affect much less, in this case, in digital PCR, that it does in qPCR. And the applications come from all these qualities of the digital PCR: detection of rare mutation, detection of rare variants in viruses, diagnosis, quantification, of course, gene expression studies. This is quite important because it's higher accuracy, and the studies of quasi-species of viruses. But to obtain all these advantages of the digital PCR, we need to apply right procedure for optimization of the protocols. And well, this is the same than with qPCR. First, we have to select the best combination of primers and probes, and the best conditions for the amplification, the annealing temperature, and the concentration of primers and probes. Normally, we use the same time and temperatures for amplification that the protocol that the manufacturers advise. Then, if we want to do it correctly, we need to apply that many assays to ensure the correct optimization of the protocol. As my advisor when I was a PhD used to say about my designs of experiments, this is a pharaonic design, which means that you have to spend lots of money and lots of time to end all the sales. But the best way to ensure the optimization of the protocol and the best reliability or the higher reliability of the procedure is to follow all these procedure to optimize the protocol. So we can select the best conditions and the best primers and probes and the best conditions. Now I want to show you how to select the best conditions in concentrations and temperature in the case of digital PCR. Here is a representation of the drops in the amplification. Here we have the positive drops, and then down in the bottom we have the negative drops. And we need to select those conditions where we have the highest difference in between the positive and the negatives, the highest distance, and the less rain, which means drops with lower fluorescence and coming down until the level of fluorescence of the negatives. Here we rejected all these possibilities because the difference in between the positives and negative influences was not that high as in this case, and because the rain was higher. And so these two conditions could be selected. We selected 900 and 500 for nanomolar for primers and probes. In the case of annealing temperature, we could use these two, but we decided to use this one because there was a higher separation between the positives and the negatives. Once we have the procedure already optimized, we start the validation of the protocol, and first step is to evaluate the repeatability and reproducibility. So we select a strain, a reference strain, and we apply from a known concentration, a known titer, we apply the serial dilutions, and then the digital PCR to calculate the number of copies per reaction that we have in each of the 3 replicas. This is the minimum we have to use 3 replicas to calculate then the coefficient of variation, which means the level of deviation with respect to the average value. So there is a difference here in between this technology, digital PCR, and qPCR. In qPCR, you use the CT values, which are in between 10 and 40 normally, to calculate the coefficient of variation. And these values are in a linear distribution. But instead, in digital PCR, we are using the copies per reaction, and these are distributed depending on the dilution in between 1 copy per reaction and 10 to the 5. 5 logs is the dynamic range of this technology. We'll talk about it later. And so we are working with data distributed in an exponential distribution. And it is known that the CV values are always higher in exponential distribution than in linear distributions. That's why for qPCR, we use the criteria of CV coefficient of variation below 10%, but in digital PCR, we use the criteria below 25%, not because we want to be more relaxed to obtain better results, not because that, but because the kind of data we are working with. After we demonstrate the repeatability of the procedure, we have to repeat the same amplification, the same digital PCR in different days or by different technicians with high, medium, or low level of experience. This is very important in digital PCR to ensure that the reproducibility is also admissible, that the method is reliable. After we have all these results, we can calculate what is the dynamic range of the protocol we have designed, and this is going to give us also the limit of quantification. The limit of quantification is the dynamic range is always must be always 5 because it is defined by the Poisson distribution that we are using to calculate the copies per reaction. And this is quite lower than the dynamic range in qPCR. This is one advantage of the procedure. The same experiments for the repeatability and reproducibility evaluation are going to give us also the limit of detection. The limit of detection is going to be below the limit of quantification and must be also below the limit of detection of the qPCR. And to ensure that, we advise the use of more than 3 replicas to get better results. As an example, in this case, we used 6 replicas for the evaluation of the repeatability and reproducibility. And you can see here that in the dilutions below -7 and -8 and below, we could not detect any positive reaction in any of the replicas. So in this case, for determining the limit of detection, we applied 14 replicas in this dilution, and in this case we obtained 3 positive replicas. You can say that using so many replicas for the diagnostic quantification is quite expensive and is it's not convenient. So we decided to calculate the minimum number of replicas we needed in this dilution to be able to detect at least one positive. This is using mathematics combinations and probabilities, quite easy to calculate it. And then we demonstrated that with 5 replicas, we would have a probability of 75% of detection of at least one positive. And using 10 replicas, it was almost completely sure that we were going to detect at least one positive. Well, using this procedure of optimization, we were able to obtain the best limit of detection ever was reported in the literature for detection of viruses by digital PCR, 0.1 copies per reaction, which is quite similar to 0.13 for parvovirus by other group. This high sensitivity is from the analytical point of view, to be sure that this method can be used in clinical samples for clinical aims. We have to test field or clinical samples to calculate the sensitivity, specificity, clinical parameters, and the predictive values. As in this example for beta nodavirus, we could demonstrate that our procedure of digital PCR had a 100% sensitivity against the qPCR, and when comparing it in the other way around, we demonstrated that qPCR was able to detect only 50% of the positive samples. So this is just to demonstrate that the digital PCR is much better for diagnosis than the qPCR. We don't use this technology only for diagnosis. We also use it for other kind of studies, like for example, this study where we are testing the capacity of this virus, the same beta nodavirus, to adapt to climate change. This is a B-segmented RNA virus, and we have 2 variants. One of them, we have many other variants, but have 2 variants which are adapted to high and to low temperature. So we wanted to see which of the segments was the determinant of the adaptation to the temperature. And we co-infected cells at different temperatures, and then we wanted to study the distribution of the segments within the progeny. With qPCR, we were not able to detect the more disadvantaged types in the progeny, but with the digital PCR, we are obtaining very interesting results. Finally, we have been talking about one of the types of digital PCR, this honeycomb type of chips. Is quite easy to understand, but the method we are actually using in our laboratory is the alternative, is a droplet digital PCR. In this case, we prepare a mixture, a mix of PCR mix, and then we have to add the miracle oil and to use a miracle equipment to obtain a mixture of 20,000 nanodrops. Each drop will have 1, 2, or 0 templates. After the PCR amplification, we use the reader, and the reader just take the sample and move it through a capillary system for the reading of each drop separately. The result is exactly the same. The advantage of this method is that we are working with 20,000 cells instead of a maximum of 5,000 cells. So the accuracy is much higher with this method. And it has been demonstrated very recently this year that the sensitivity is also higher with droplet than with cheap digital PCR with a limit of detection much lower in all cases. This is all. I want to thank all my people in my group, and mainly to the ones which are the experts now in digital PCR, who are the research assistants. Thanks a lot for your attention. Well, any question you have, don't hesitate to place it.